Section 1.3 says evaluating limits analytically. Analytically is another word for algebraically. So those of you who are like, can't I just plug the number in? This is the lesson for you. So we're going to take a look at some different limit rules and properties in this section, and some processes that allow us to, in many cases anyway, plug values in to find limits instead of generally looking like at a graph or a table of values. So when it works well or nicely, this works quickly. So let's take a look. Some basic limits first. B and C are real numbers, and is a positive integer. So if we have the limit of B, where B is a number, so you guys actually saw this happen on one of your homework problems. Several of you came to my office to ask me questions about it. The question said the limit of -1. And the answer is -1. So whatever the value is, the limit is that same value. And that makes sense from a graphical standpoint. I know that some of you were describing this to me from a graphical standpoint. If you have an equation, and the equation is y equals some number. That's not a hashtag, by the way. It's a number sign, just so you know. It means that you have a graph that's a constant line, right? It doesn't change. So at every point along that line, the y value is the same. Whatever it was, it's the same. So the limit is that same y value. So on that particular problem, it didn't matter what the epsilon and the delta were. It made no difference whatsoever, because the constant value is never going to change for the y on that one. On number 2, the limit as x approaches c of x is c. And again, I'm going to justify this from a graphical standpoint because it's fairly easy to see. If this is the line, y equal x, the line y equal x means that whatever y is, x is, and vice versa. So if it's telling you that x is really, really close to c, then clearly y is really, really close to c because they're the same, right? The last one I don't have a good graphical justification because it's so general, but the limit of x to the n as x approaches c is c to the n. And you see that same sort of a sense of we're just evaluating the function there. And the reason all three of these work in general is because these are continuous functions. Don't have any holes, don't have any jumps, they don't have any piecewise anything's going on. They're just, they're well behaved. We use that word sometimes too. They're well behaved functions. Now there are some properties of limits that we're going to look at next. I think I have 5. Yeah, 5 properties of limits. So again, b and c are real numbers and n's a positive integer. F and g are functions that do have limits. So this stuff doesn't necessarily work if we have infinity as a value we're approaching, okay? We've got to have numbers here, like a constant number that we actually have a limit for. So if the limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is k, then if we multiply f of x, we're going to multiply the limit value. So what you're seeing present here, it's not going to work, I don't know, is that this f of x and this L, when we get close enough, are the same value, right? They're going to be very, very close together, and the b value, this constant that's being multiplied, is simply multiplied by the limit. Sometimes you'll see this written like this too. You'll see them write it as the b in front. Some textbooks will, as x approaches c of f of x. In other words, it doesn't matter if you multiply the function or if you multiply the limit on the outside, you get the same result. And if you have two functions that are either added or subtracted, and they both have limits, then their limit values can be added or subtracted. And you can do them sort of piecewise. And I don't mean piecewise as a function so much as just one piece at a time. And nicely enough, the same thing holds true for multiplication. So addition, subtraction, and multiplication always have this property. If I have limits for them, I can just multiply or add or subtract the limit values themselves. Okay, two more. Quotient and power. The quotient division, same thing as multiplication, addition, subtraction with one caveat, and that of course is that the denominator can't be 0. So whatever the limit value it is for g of x itself, that can't be 0. Right, so no zeros in denominators as always. That's an undefined value. But as long as g of x's limit's not 0, it works just like the multiplication, addition, and subtraction. And then, of course, you see the power rule acting very much like the very specific polynomial one that did earlier on in our other set of basic limits, is that if you have the limit as x approaches c of f of x and it's raised to a power, it's just the limit value that's raised to that power. So, all of those things are going to be working behind the scenes. They are what allow you to plug numbers in. So you're not even going to feel like you have any use for these, but you're going to be using them intensely. Every time you take a number and you simply substitute that number into the function, when you're able to do that, you're using these basic limit properties. You're just not thinking about it as you're doing it because you sort of feel like it makes sense. It's a natural approach. All right, but these are what's working behind the scenes that are allowing you to do that. So we're going to do a couple of examples, finding the limit. So again, on this one, you see two functions that are added together, so you're using that addition property. You see a power rule, you're using a power property. But the reality is that what you're going to physically do is evaluate. You're going to attempt, when possible, to simply plug the value in. Because when a function is nice and continuous and well behaved, the limit value is the function value. So, what is this value? It's 0. Remember, we're squaring the 1, not a negative 1. It's just squaring the 1 that's in that parenthesis. And then we've got the negative acting on it afterwards. So it's 0. Now raise your hand if you'd rather go back and do a graph or a numerical table. Probably not. Right? This is so quick, and that's very friendly. Second one, again, if we're able to do it, and then we have to check to make sure. If I have a 0 in the denominator, I'm not going to be able to do this problem like this, right? Is this value, x approaching -3, going to make my denominator 0? Nope. So I've got the quotient rule here, I've got an addition rule here, I've got a subtraction rule here. I also have a constant multiplier rule here. This 2 at the beginning, that's that B rule from the very beginning on the first one of the 5 at the very last slides. So I'm using all of those rules, I just don't even feel like I am. So I'm going to evaluate this at -3. So I need to see that you've plugged the number in, okay? I realize that for the most part, these are pretty straightforward. You're not going to make a mistake, but if you do, I have no way of giving you partial credit. So show me the number that you've plugged in so that I know that you're approaching the problem in the right direction, and then you can simplify whatever steps or however you want to use your calculator at that point, okay? So what do we have on the top for this one? It's -9, good. And the bottom? 2. And that doesn't simplify. I think probably by now you guys realize that improper fractions are more friendly than mixed numbers. My elementary ed people still don't believe me on that one, but they are for mathematicians, for scientists. So leaving this as is sort of preferable. Fractions also tend to be easier to work with than decimals from a scientific standpoint, mathematical standpoint. So most of the time we'll leave them in a fractional expression. All right. Theorem 1.3. Limits of polynomial and rational functions. If p is a polynomial function and c is a real number, then the limit as x approaches c of p of x is p of c. So polynomials. Can somebody give me an example of a type of function that you know is a polynomial? Anybody remember any? Lines. Lines are polynomials. They're not very exciting. Parabolas, quadratics, those are polynomials. X cubes, x to the fourth, x to the fifth, all of your power functions, okay? Those are polynomial functions. So as long as you have a polynomial function, the limit is the function value, always. Rational functions are functions that are in ratio form. So you have a polynomial divided by a polynomial. And when you have a rational function, as long as the denominator is not 0, again, the limit value is the function value. So polynomials and rational functions are very well-behaved functions. They do what we want them to do. They are as expected. The next type of function are radical functions. So again, radical functions are well-behaved functions. If n is a positive integer and you have the limit of the nth root of x as x approaches c, it's the nth root of c. The limit value is the function value. We do have some sort of catches, right? The limit value itself needs to be appropriate for the function that you're working with. In other words, if you have a square root, you don't put negatives underneath it. So that's what this is saying at the bottom. It says for all c where n is odd, so as long as you have an odd nth root like a cube root or a fifth root, you can have any c value. But if you have an even root like a square root or a fourth root, you can only have positive c values because you're plugging them in underneath the radical. Composite functions. If f and g are functions where the limit of g of x is L and the limit of f of x is f of L, then the limit of f of g of x equals f of the limit of g of x is f of L. If you remember, composite functions are one where we take a function and we plug it into something else. So for example, we just talked about radical functions on the previous slide. If I put a polynomial underneath a radical, I'm good to go. Because polynomials have this well-behaved feature, and I'm plugging them into a radical that has a well-behaved feature, so I'm still good. This expands to lots more types, many more types of functions because of this feature. Okay, being able to put one function inside of another one. Also means you can put radicals inside of rationals, right? The denominator and the numerators. All that good stuff. And so we're going to do some more limits. Much like on the last two that we did, our goal, if we're able to, is to plug the number in. So this is a rational function. I do have a polynomial on top and a polynomial on bottom. And with rational functions, I do have to be a little bit careful about what? The denominator not being 0. So if I plug 3 in, what will happen to this particular denominator? It'll be 0. Okay? So what do we do when that happens? What do you think we might do? Factor. Yeah, we're going to try and simplify and factor. So let's take a look. Rational functions is where we see a lot of this happening. So we're going to do several rational functions here. We need to simplify. Now, the numerator, I mean, we can write it as 3 minus x. That's fine. But the denominator, it can be factored, right? How will x squared minus 9 factor? You got it. X plus 3 and x minus 3. Here's the deal. None of those factors are exactly alike, but 2 of them are almost alike. Can you tell me which 2 are the most similar? It's not the x plus 3. It's the other 2. How are these related? Any idea? The symbol is in the reverse order, right? They're subtracted. One of them is a negation of the other one. It's a negative. So the reality is that they do get to cancel out, but when they cancel out, you're going to get a -1 factor in it. Because if I were to multiply one of them by -1, I'd have the other one. right? It's like having a negative 3 over a 3. Well, they cancel out, and you're left with the negative. Another way to see that, if you're not liking that, like that just kind of feels awkward, is what you could do in the numerator instead is to factor a negative out, which would actually give you x minus 3, exactly like it is in the denominator. And then you can reduce those two perfectly, leaving the negative there. All right, here's something I want you to notice. Check and see if you did it. Did you rewrite limit x approaches 3 when you factored? Okay, you need to. If you write equals next, they're not equal statements. Equals does not mean and the next step is. Equals means two quantities that are exactly alike. So if there's a limit on one, there's a limit on the next one until you actually plug the number in, if you're able to do so. So we need one more step where I'm going to write what I've got currently. What I've got currently is, negative 1 over x plus 3. And now, is my denominator okay? It is. No problems now. I can actually plug that value in, and it works just fine. And I end up with negative 1 over 6. So what happened? We talked about this briefly on a different day. I think it was last week sometime. Well, it was last week sometime. I think it was Monday, actually, or Tuesday. I mean, we have a hole in the graph is what we really have. When we have the ability to cancel things out like that, it creates holes in graphs. And so holes are okay. It means that you can get infinitely close to something. You just can't actually land there. All right? So limits exist. The function value doesn't exist. There is a hole in the graph, but the limit's okay. And that's what's happening when this happens. How about the next one? Check the denominator, right? We're working with a rational function, so check the denominator. Can I plug the denominator, or plug the value into the denominator? No, it gives me another 0, right? So we're going to do the same thing we did on the last one. We just have more to do because the functions themselves are both polynomials that can be factored. So we need to factor the numerator and the denominator on this one. So let's check it out. Somebody tell me what you get when you factor the numerator here. X minus 4, x minus 1. That looks good. Does that look okay to you guys? Nice. How about the denominator? Good. X minus 4, x plus 2. If you're a little rusty on your factoring, I'm going to let you figure out how to brush up on it on your own. Come see me if you want. That'll be fine, but we won't have time to do it in the classroom, okay? So, what do you notice? Yep, there's an x minus 4 on top and bottom, right? We're still writing limit, right? Limit's still there. One more time. Limit as x approaches 4 of x minus 1 over x plus 2. Am I good to actually take the 4 and evaluate now? I am. So I have 4 minus 1 on top, 4 plus 2 on bottom, which gives me, 3 over 6, 1/2 when I reduce. Good job. Okay, so factoring. That's a thing, and we're going to need to use it. The next problem is substantially different, but I want to show you that it has some similarities to the ones we just did. I can't plug the 0 in the denominator, right? So that makes it similar to what we just did. I have radicals, however, which makes it a little bit different because factoring the numerator is not going to work here. Agreed? So what I'm going to show you is actually how to handle a problem specifically with radicals, okay? So you've learned a long time ago that we don't leave radicals in denominators, like square root of 2 doesn't stay in a denominator. Trig is where it's usually hit really hard. No leaving square root of 2's in the denominator kind of thing, and you have to rationalize denominators. Shake your head if you remember that phrase. Okay, good. What we're going to do on this problem is we're going to rationalize the numerator, okay? I mean, I have to get that x in the denominator to cancel out, or I cannot plug the 0 in. Everybody understand that? I got to get it to go away. The only chance that I have is to manipulate what's on top to try to figure out if there's a way to change it to have that x as a factor. So what we are going to do is to rationalize the numerator. So rationalizing means taking our radicals and eliminating them. So right now, my two radicals are x, square root of x, 2 plus x, and square root of 2. And what I'm going to multiply by is called the conjugate. The conjugate looks exactly the same, but with the opposite sign in the middle. But if I do something to the numerator of a fraction, I got to do it to the denominator as well. Now, I really do not want to multiply this through the denominator. I really want to leave it as it is, because my goal is to get the x to go away anyway, right? So I'm not going to clean the denominator up, quote unquote. I'm not distributing, I'm not doing that. But I do get to distribute in the numerator. So let's take a look at what the distribution of the numerator would look like. So, whoops. When I multiply square root of 2 plus x times the square root of 2 plus x, what do I get? Yeah, x plus 2 or 2 plus x, right. And when I multiply the last two terms together, square root of 2 times square root of 2, what do I get? A negative 2, right? Negative because one's negative and one's positive. Now, of course, what you remember from an algebra course, I'm sure, or from rationalizing in trig, is that you have to multiply first, outer, inner, last, or you have to do distribution, so you'd also multiply these two together and these two together. The reality is that when you do that set of multiplications, you get the exact same thing, but one of them is positive and one of them is negative. Can you guys see that okay? So the outer terms, when they're multiplied, are going to cancel out with the inner terms when they're multiplied. They add to 0. And that's what the beautiful thing is about. What this really is it's a difference of squares in practice. So we actually see the inner and the outer terms cancel out, which is why we don't have any radicals left. All right, so denominator. It still has an x, and it has the square root of 2 plus x plus the square root of 2. But what do you notice that the numerator has happened next? What's my numerator? Yeah, the 2's cancel out. They add to 0. So there's that x and this x that can then divide out, right? You divide both the numerator and denominator by x, leaving you with a 1 on top, and technically there's a 1 here as well on bottom. As a factor, it's not ending up, being all that useful. But this gives me the limit as x approaches 0 of 1 over the square root of 2 plus x plus the square root of 2. And now I can plug the 0 in, can't I? I can. So now, again, this is the first point in the problem now where I get to eliminate and don't have to write the limit part because I am actually evaluating it. I have 1 over the square root of 2 plus the square root of 2. Now we're going to do some cleanup from the algebra here. So what happens when you have square root of 2 plus the square root of 2? Yep, that's 1 over 2 square roots of 2. Just like in trig, we're not going to leave that square root of 2 down there. So we're going to rationalize one more time. So I have the square root of 2 on top. What's on bottom? 4. These two are 2 when you're multiplying together times the 2 that's already there. So I have square root of 2 over 4. All right, no discussion would be complete on limits without some trig stuff. So trig functions, where they have domain values, are also well behaved. So the limit for sine, as x approaches c, is sine of c. Cosine is cosine of c. Tangent, cotangent, secant, cosecant. Everything just like you would expect. Okay, there are two special trig limits that we're going to look at as well. They're not just directly these. The first one is what happens when we have sine of x divided by x. It's very specifically sine x divided by x. If you were to evaluate this, if you were to try plugging 0 in, does anybody remember what the sine of 0 is? It is 0. And obviously if I plug 0 in the denominator here, I get 0. So on this particular instance, 0 divided by 0 is 1. Okay, you didn't hear me really say that. That was sort of a joke, right? Like it's not 1, right? Like we get that. It's undefined. But that is what this limit value is. And we will talk more later about why that actually works out. For right now, we're just going to take it as a fact, but we'll get there. And the other one looks kind of like it's got some sort of a trig relationship to it, right? Because I also have 1 minus cosine on top over x. And we do know that there's a Pythagorean relationship between sine and cosine that this sort of feels eerily like, right? Sine squared plus cosine squared equal 1. And that is working behind the scenes here as well. But this limit is actually 0. So when we see these able to be used, we will be able to use them. Right now we're using them at face value, okay? So let's do a few more limits before you guys fall asleep with the heat in the room. I can tell you're struggling. I'm struggling. It's warm, isn't it? Okay. So on this one, it has the limit as x approaches 2 of sine of pi x over 2. So this isn't a special limit, right? I don't have sine x over x. This is just one of those first 6 that you wrote down. So because we're able to do so, it's a sine function I'm simply evaluating. So sine of pi times 2 over 2 reduces to what? Sine of pi. And now you get to try and remember some trig. What's the sine of pi? It's 0. And who was it? Emma, was it you that asked me during the quiz about radians and degrees? Yeah? Okay. When we're working with trig inside of calculus, we're always working in radians. So if you want to go ahead and change your calculator to radians, you're never going to need degrees. It's never going to happen, okay? All of the calculus functions that we're going to work with related to trig are all based on using radians because radians are real numbers and we're working in the real number system, okay? So the next one, we can plug it in, right? Now we'll really test your trig knowledge. What is the cosine of 5 pi over 6? What is it? Yes. So here's where it might be a good idea if you don't have one sort of at your fingertips and maybe you're a little rusty on the values from trig. I would encourage you to go out online and just Google unit circle and print it out. Okay, there will be images all over there, unit circle images if you want or something like that. Print out a unit circle and have it with you as you're working through until you're good and comfortable at remembering those values because they're going to come up from time to time, okay? Have them with you. All right, now, what happens on this one if I try to plug 0 in? Yeah, I get 0 over 0, right? So it is going to be 1, but not exactly. You're thinking about using this one right here, this property. Is that right? You're right. We're going to use this property, but there's still a 5 here. Not quite. We're going to factor out that 5. So here's what we're literally going to do. We're pulling a 1/5 out in front. And it might look a little bit like magic, but it isn't. We had a theorem at the very beginning that said that we're allowed to do that. I'm going to go back to it on my slide, in fact, so. That property number 1, do you remember that? And I said you can pull it out in front. That's what we're doing. We are taking that 1/5 factor and we are pulling it out in front on this particular problem. And it's cool because then I do have that limit of 1 there. This is 1. So what is 1/5 times 1? It's 1/5. Okay. Number 9. What happens on this one if I try to plug 0 in? Got a 0 in the denominator, right? It's no good. Cosine of 0 is what? It's 1. And what's the tangent of 0? It's a 0. So if I try to plug this in, I have 1 times 0 over 0. That's not good, right? But it doesn't sort of perfectly match either of these, like the other one. The other one almost felt like, oh, look, there's just a little extra 5 there. I don't know what he's doing there, but otherwise it matches. Do you have an idea, Connor? Yes, indeed. So, yeah. Which one did you have in mind?
Cosine x tangent x equals sine x.
I'm sorry, say it again one more time.
The numerator equals sine x.
The numerator does equal sine x. So, let me write by that part first. All right, so limit as x approaches 0. The cosine is still there. And then what is tangent? It's sine over cosine. Yeah, sine over cosine. And then I've got the x in the denominator. I don't think that I've posted them yet inside of our Canvas classroom, but I will. I will post the basic trig properties that might be useful for you. It'll have Pythagorean ones, quotient ones, reciprocals, and a couple other things that might come in handy. It's what I hand out when I'm working in trig, so I'll post that so that you have that as well. If you'd like to print that out to have that as a reference, you'll be able to use that. Of course, the whole point of this is that the cosines cancel, right? So cosine here cancels with this cosine, which leaves me with the limit as x approaches 0 of indeed sine x over x. And what's that? It's 1. It's 1. So you're going to have some trig manipulation in some of these problems. You're going to have some limit manipulation, right? Moving around with limit rules and things as well in these problems. And that is the rest of the lesson.